Harry?
I think it's for refraction.
Yeah. We are. We're back to physics. So the question was, what is this formula? Where does it come from? Sine inverse of nr over ni?
Yeah, what's it used for?
Yeah, so this is used to calculate the critical angle necessary for total internal reflection. And if you recall, the critical angle is just what the incident angle needs to be to cause that. So for example, if I have two materials and a light ray is coming through this one, and I have my normal drawn right here, if I can exceed, or if the angle incoming exceeds what we call the critical angle, this light ray will not pass through, but it will bounce back in. So this is the angle necessary on the incident side. That's what it is, really. So if I know, let's see, let's say we're going from, we'll say this is Ni. Ni has to be bigger than Nr for this to work, by the way. Let's say that Ni is 2.7 and Nr is 1.3. And I have the formula, right? Nr over Ni, right? So if we're looking at this, what we're going to do is be able to see that we go from a material with a high index of refraction to a low index of refraction. When this decreases significantly, what's going to happen is the refracted angle is going to increase significantly. So if I come in at a certain angle, I might get a refracted angle bigger than 90. That would cause total internal reflection. If I want to figure out what that angle is, I could just use this formula though. So I could try a number first. So let's do this first. Before you use the formula at the top, do this. Ready? Let's hypothetically think that this is, let's say 50 degrees. If that's 50 degrees, this angle is going to be much greater than 50. It's not going to continue along the path you would think it would, but it's going to bend outward. We know it's going to become a larger angle because the index of refraction went down, and we talked about that correlation the other day. So tell me real quick, what would theta r be in this case? And again, I don't really know what it is, so I'm going to erase this for now because it's not really true. We're not sure. But if I solved, and again, don't use this formula. We'll use this in a minute. Don't use that now. Use instead of using the critical angle formula, use Snell's law and come up with what theta r would be. Okay, theta I is given, the initial angle or the incident angle, right? Incident angle is 50 degrees. It's going to hit a material that has a lower index of refraction, so therefore the angle of theta r is going to get greater or larger in this case, right? It's going to become larger here. What's going to happen if we solve for theta r in this case?
Because I got Nr is over 1, so that's not even refracts.
So the reason you're getting an error here is simply because this angle is going to become greater than 90. So the angle of 50 degrees coming in is too much already. Again, the angle of 50 degrees that's coming in here is too much of an angle that this refraction is not even going to occur. It's going to cause it to bounce back into the material. So if you want to, just to check, try another number. Instead of 50, try 40 up here. Try 40 for theta I and see if you get an answer now. You still get an error, right? Try 30. Just press second enter, right? You're doing it that way? Just keep repeating it. What do you get when you try 30 instead? Oh, you're close. All right, so try 25. So all of these angles are causing internal reflection. That's the problem we're having. But if we try something small enough, like 25 degrees, hypothetically, what do we get? We got it. All right, so if I had a 25 degree angle coming in, it would cause a 61 degree angle after it's been refracted. Remember, this is the normal continuing. This angle here would be around 61 degrees. So the issue is this. I was doing this on purpose to prove to you that you don't want to sit here and try them, right? Nobody wants to try all these angles and say, well, what angle will cause the error? So Anthony could try 26 degrees, 27, 28, 29. 29 will probably work still. When he tried 30 a moment ago, though, he got an error because the angle exceeded 90. So instead of trying these angles over and over again to see which angle would cause this to bend enough, and remember, when it bends enough, it means this angle, instead of being 60, instead of being 70 or 80, instead of being actually 90, the angle is more than 90. So you end up getting a ray that does this, and it stays inside the material. It becomes greater than 90. So the question is, how do I find out what this angle necessary is to cause this? And that is where this formula comes into play. The formula at the top is used to figure out what angle is necessary here to cause this angle coming through to be greater than the 90 here and to bounce actually back into the material. So calculate theta C real quick.
If it bounces back in, does it have the same angle as if it's going in?
No, it's not the law. It's not like the law of reflection where the angle coming in is equal to the angle going out. The angle that it refracts at is a function of the materials and their indices of refraction. You got an error? Sine inverse of 1.3 over 2.7?
Oh, I did.
You did 2.7 over 1.3.
I got 28.8.
Yeah, so anything higher than 28.8 would cause total internal reflection. Well, a moment ago, Anthony tried 30 and it didn't work. And I said 29 will probably work. It turns out 29 won't work. 29 will also give us an error. But you said that theta critical is 28.8. So any angle that exceeds this number up here, this 28.8, will cause the light ray not to pass into the next medium, but to bounce back into the medium it started in. Again, anything greater than 28.8, so let's make this 30 hypothetically, or 31 or something like that, would cause this ray to bounce back in and stay inside the first medium instead. It would not pass through, it would be internally reflected. Even though it's refraction, it's the bending of light actually, we call it total internal reflection because it's being internally reflected. Okay, it's not like it's on a surface that's bouncing it off. It's being bent enough that it bends back in. The name could be a little bit of a misnomer, I guess, right? Total internal reflection, even though it's refraction that's occurring. That's where the critical angle comes into play. What else do I do? We've done a lot, right? We really have. We've done a lot in these review days, which has been really good. We worked on the formula sheet for a while. We worked on example problems. The other class did a bunch of different example problems. So again, look at the other classes' stuff also if you want to study a little bit more. We did example problems in their section that they posed that were probably quite different from yours, or they were quite different. Some general themes the same, but different problems. What do you think? What should we do? Pick a topic. What's something you struggled on earlier in the year that you want to go over? Yeah, what do you got?
I know we just did this, but can we go over like the temperature,
Yeah, do you want to do one with like, you take a piece of metal and drop it in water, or one where you add heat to a substance and it changes its phase? Change of phase? Okay. So for a change of phase problem, the first thing you have to identify is the boiling and the melting point of the substance. So let's call this substance X. Okay, and I tell you that substance X has, let's see, a melting point of 20 degrees Celsius and a boiling point of 85 degrees Celsius. So it's not water, but maybe it's something like water, some sort of solution. I also tell you that the C value is 2.5 times 10 to the 5th, and that the, what else do we need? Let's say for now, LV and LF we need also, both of those. Well, it should be back, actually, let's write them the other way so we're not confused. LF is first because that's like the melting one for fusion. V is for vaporization. Let's say LF is 5 times 10 to the 6, and LV is 7 times 10 to the 6. Units will be given, obviously. You'd be given the values on a table or some information in the problem. So let's take a look at this problem and just go through the setup. I'm assuming, by the way, for this problem, that C is the same for all of these different states, whether it's gas, liquid, or solid. With water, though, you guys already recognize this on your test and on your homework and on your problem set, on your example in class, on your formula sheet or the reference table. The C value for water changes if it's ice or water or steam. So please be careful of that. Some of the mistakes on the test came from that. So C is a specific heat capacity. It's the amount of energy needed to change the temperature of a substance. But depending on the phase of the substance, that C value can change. Here I'm saying that the C value is constant for this substance in general, no matter what the phase of the substance. So let's say that we're going from negative 50 degrees Celsius to 78 degrees Celsius. So we have this substance at negative 50 degrees and we want to bring it up to 78. Step me through what has to happen physically for this to happen. What has to happen, again, physically for this temperature change to occur?
I mean, it's going to go through, once it gets to 0, it's going to change phase.
At 0, yeah? Are you sure at 0? Where does it change phase? This is not water. This is some random substance. Sorry. Take a look at the board.
It's going to change phase at 20.
Yeah. So what does it start as? What kind of a substance does it start as? If it's negative 50, is it solid, liquid, or gas? Solid. And then what happens at 20, Joe? It melts. Bless you. It melts, okay? So Q1 is going to be MC delta T because we know that there's going to be a change in temperature until it gets up to 20. So we're going to have final minus initial for the delta T right there. Final is 20, initial is negative 50. Again, I'm doing this in stages. I'm truncating the problem. I'm saying in the beginning, we have to raise temperature. Then after that, we change phase. After the phase change, we'll see another increase in temperature. That's what's happening here. So we think of this in 3 pieces. Increase the temperature, change the phase, keep increasing the temperature, maybe change the phase again. But that's the process we're going to undergo. The M value would be the mass of the substance. Let's say we have, it doesn't really matter, 2 kilograms of the substance. And the C value is 2.5 times 10 to the 5th. So that's the energy necessary just to warm up the substance from negative 50 to 20. Not the energy needed to melt it, just to get it up to 20. That's how much energy would be necessary.
And you'll give us the substance, right?
Yeah, you'll be given either like a table or you'll be given the values in the problem itself. Okay? How about Q2? This could also, by the way, this could also be a multiple choice, a very simple multiple choice. Asking you guys about different parts of that graph, asking about what physically happens. It could be a short answer, where I give you something like this in the beginning. Remember what Alejandro said? I said, what has to happen here? He said, well, it has to get up to 20 and then melt. And then maybe what happens next? Then suddenly it goes through a phase change. Then it has to go up to 78. See this little diagram right here? This little like truncated diagram? This is a great explanation for like a short answer kind of question, not a mathematical. What would physically happen to this substance? Well, temperature would increase, then it would melt, and then the temperature would increase more. That'd be a great explanation of physically what's happening. So this problem could be asked in 3 ways. It doesn't have to be mathematical. Okay, keep that in mind. Q2. MLF. Why F and not V?
Because it's going from a solid to a liquid, so that's fusion.
Yeah. Solid to a liquid or liquid back to a solid is called fusion. When it goes from a liquid to a gas, you think of a vapor, like water vapor, hence vaporization. That's what the V stands for. So we're going to use LF, F for fusion. And all we have to do is take the mass times LF, and that will give us the energy necessary to change phase. Why isn't there a delta T in this formula for Q2? Who's been able to figure that out? Why isn't there a delta T? There's a delta T here. There's going to be one here. Why isn't there a delta T here? Shouldn't there be some sort of change in temperature for heat to occur? Why not?
It was like during phase change, the temperature like stays the same.
Yeah, the temperature stays at 20 during that phase change. It gets up to 20 during this part. It stays at 20, and then it increases from 20 on afterward. So this last part is going to be, again, MC delta T. Delta T is going to be different, though. But M and C are the same. What's delta T in this case? What's the final temperature? What's the final temperature this substance will reach minus the initial in this stage? Within this stage. What do we got? What do we got? Same couple of hands. I want to see others here. Come on. What's the final temperature this is going to reach? Just look at the problem itself. What do you got, Emma? That's what it could reach before it changes phase. It could only reach 85 before it boils off, right? What do you got? 78 though. Very good, Emma. Emma noticed, well, it's only going up to 78, so it's not going to boil. So it's not going to reach 85. It's only going to reach 78, and it started at 20. Be careful, not negative 50 here. We already took into account from negative 50 to 20 in the first stage. So now we're at 20 degrees. We change phase, and then we go from 20 degrees up to 78 degrees. Had this been a problem that went higher than 85 degrees, this substance would have also boiled. It would have also boiled. And then possibly, depending on what it went up to, say it went up to 90, it would have boiled. Well, this would have gone up to 85, then Q4 would have boiled, and then Q5 would have gone from 85 maybe up to 90 or wherever else it went up to. Again, very, very heavily conceptual, although there's math involved. All right? Add those three numbers together to get the overall heat necessary to perform this operation, whatever. Good question, Katie. What else? What else? Look at your review sheet if you want to. Just at least look at the topics. By the way, I think there was a typo in the review sheet, just so you're not thrown off guard. I did 35 multiple choice on the test, not 30. I think it says 30 on there. Okay, they're still worth 1 point each. Okay, but the only difference is that you have 35, not 30. And the short answer, you have fewer short answers. Because last year, a lot of students, not a lot, but last year I think there was a time issue for sure. Like students finished, but I wanted to give a little bit more time to check over the test and stuff. So I added 5 multiple choice, but removed 5 short answers, or 4 or 5.
Short answers?
I think it's actually 11 short answers in the end, because they're worth like either 1, 2, or 3 points. So it just has to add up. It adds up to 25 points for short answer, and 35 points for multiple choice. And then the math is still the last 40 points the same way.
It's like a free response question.
Here, how about a sample free response? Let's look at something like momentum. This would be a good example, okay? Great example for the test, I think. So let's say we had a mass on this end and a mass on this end. And the first mass was 8 kilograms, and the second mass was 5 kilograms. How fast was the first mass moving? Theo, what do you want to, how fast you want to make the first mass?
Let's do 10.
All right. 10 meters per second. We'll say to the right. And we'll say that the second mass is not moving initially. So we write V2I is 0. And the question becomes, it's two-part question. A, determine the speed of each object if the collision is elastic. Second, determine the speed of the system if the collision is inelastic. Determine the speed of each particle after the collision if it's elastic. Part 2, if it were inelastic, determine the speed of the system afterward. Theo, help us out. What do we got?
So we're going to use the formulas M1 times V1I plus M2 times V2I equals M1 times V1F plus M2 times VF.
Okay, that's exactly right. And why do you start with this formula for part A, Theo? What did part A say?
Well, because even in the wording you said defining each velocity, so in the other equation, which is, it starts out the same, but then it goes equals M1 plus M2 parentheses, and then they're together, and then there's VF, and it's only one velocity, so you didn't know like which one's which, you can tell.
Yeah, you don't even need to know the word elastic and inelastic in that scenario if you think about it. Theo's exactly right. The wording of the problem said, find each velocity after the collision. And then I was nice enough in part 2 to say, find the velocity of the system after the collision. Okay? Now, the first part is elastic. It's elastic. So all we have to do is go ahead and plug in. V2I is 0. It's not moving, so that drops off. So let's drop that off right away. Then we can plug in. If we want to go ahead and plug in first, M1 times V1I is going to be 8 times 10, or 80. M1, oh, we have to have, sorry, we should know something else. What else do we need to really know? We need to know one other thing. Because we have two unknowns now, right? We're missing V1F and V2F right now, both. So let's say that the second particle, or the second object itself, after getting hit by the first one, shot off with a velocity of 13 meters per second. You have to be given another piece of information in order to solve, unless you use kinetic energy balance. You could technically, but we didn't really go into that a lot, so I'm not going to push that. So M1 V1F is the one that's unknown. We have 8, and we're missing V1F. M2 V2F is going to be 5 times 13, or simply 65. Again, take a look at your variables. This is the momentum of object 1 before the collision. The momentum of object 2 before the collision is 0. The momentum of object 2 after the collision is 65. That's the 5 kilograms times the 13 meters per second. What's unknown is the velocity of the first object after the collision. Okay, I shouldn't have said each, I guess, then. So let's just make sure we correct that if you were looking at the wording, okay? It would have said find the velocity of the first object if the second object is moving with a velocity of 13 meters per second after the collision. So all this would be is solved for V1F. Subtract 65 to get 15. Divide by 8, you'll get around 2 as an answer. Okay, 1.875. Now, if they had stuck together, Theo already mentioned it, but somebody else, please help me. If they had stuck together, how would this problem change? So now this is no longer here. Okay, 13 meters per second is not really there. These objects are now sticking together, so we don't know that. Emma, what do you got?
M1,
Oops, my typo, sorry. Go ahead, keep going.
plus M2, V2I, equals M1 plus M2 times the final velocity.
So all we do is lump the masses together on the second half of the equation, because these two objects eventually or end up sticking together, and then they move as one afterward. And they move as one as they move as one afterward. This still drops off and goes to 0 because there was no velocity of the second object to start. We know everything else. This is still 80 from earlier, plus 0. I don't have to even put that, obviously. M1 plus M2 is going to give me what? 8 plus 5 times VF. So 80 over 13 is going to be your answer. Okay, 80 over 13. And that'll be in meters per second. How would this change if, ready? Think about this for a second. How would this change if I think about, imagine I'm a police officer, or somebody who is supposed to be using a gun, a hunter, who knows, somebody that's hunting like wild game. And you're hunting with your rifle or shotgun or whatever it is, and when you shoot the gun, you notice that the gun kicks back, right? It's like the first thing that happens, it kicks back. So, if I were to shoot a bullet out of a gun, how would this scenario change? Think about the physics of the situation. You shoot a bullet out of a gun.
So the bullet would be M1,
Good. And the gun is?
M2.
Okay. And how would the equation itself change? Like how would this, like just look at the setup.
The mass.
Forget the 0 part, obviously. Just
The mass would be a lot smaller and the velocity would be a lot bigger.
Okay, you're looking at the physical nature, but I mean just like how would the equation physically change? Like, this would not look the same. It would not be the exact same written solution here for this equation.
Is it because the gun stays stationary for the whole time, and that the
Well, the gun will have a little recoil. Assume there's recoil on the gun. If the gun were to stay stationary, it'd be a difficult problem. It's impossible for the gun to really stay stationary. It will move a small amount, no matter what. Even if your shoulder absorbs the impact from the impulse.
what if it was like mounted?
Does this have to?
It's still, even with that, you're still going to have like natural recoil. And And I'll explain why that is.
I think the velocity.
Not really with that part.
So I think like the two objects go apart, so you can't really use that equation because
This equation shows when they come together, right? Well, class figured it out. You shoot a bullet out of a gun, don't they start together? Doesn't the system start together? And then you shoot the bullet, and then doesn't it separate? Who did I invite up? Was it Natalie and Anthony? There's the two, right? And you pushed off. That's the gun and the bullet. You start together, and you push off and separate. So what's the momentum of the system when you start off is 0, because you're starting off at rest. Hey, you're holding a gun, the bullet's stationary, the gun's stationary, the momentum is 0. Ben, this answers your question. So the momentum is 0, right? I fire the bullet. The bullet has momentum that way, so the gun has to have momentum this way. Follow? So no matter what, even if the gun is actually fixed, there is still momentum kicking back, but the object might absorb the force, so the impulse is very, very low. Okay, but there is still momentum because of conservation. Conservation of momentum tells me if an object moves this way and it separates from a stationary whatever combination of two objects, the other object has to move this way by default. Okay, so for momentum, you need to think about scenarios. Start together, separate. Start separate, end up together. Start separate, hit, end up separate. Those are really like our 3 scenarios. 2 of those are inelastic. Whenever the things stick together, or start sticking together, or end up sticking together, inelastic. When they hit and bounce off, elastic. Think elastic. Elastic is bouncing. Something that's elastic is bouncing.
So is this like that spaceman problem? Where like
Yeah.
the fire extinguisher?
Yeah, the question is like, you're stranded, or you're about to float away from your spaceship because the cord got cut. How do you get back to the spaceship? Well, you throw an object that way, it'll push you back this way because of momentum conservation. It'll push you back to the spaceship if you do that. You could, who saw Gravity? I think there's a scene in Gravity with the, isn't it with the oxygen tank?
That movie made me so anxious.
It looks like a fire extinguisher, but I think isn't it the oxygen tank she uses? Or he uses, or somebody uses? I forget.
She's like in a chair, right?
But she's outside the space shuttle. She has to like direct herself back to the space shuttle with the oxygen tank or
Oh
something.
yeah, it is the accident.
It acts as like a thruster, as like a rocket would. The same concept as if you threw something that way, you would naturally move the other way. I gave you an example on an old test where it was like a rich man is stranded on the middle of a lake and he's got a bag of gold coins. Let's assume the lake is frozen and there's no friction. How does he get to one end of the actual lake? Because without friction, you can't step. So as you guys said, you throw or push the coins that way, which way do you go? The other way. Some people said, put the coins down and push off. You can't push off, there's no friction. Right? You have to actually throw it or move it. And I mean, by push off, I mean people said like, put the coins down and it'll be fixed to the ground and you could push off on the coins, as in the coins will be like a barrier like this, it won't move. You'd have to literally shove them the other way with velocity so you move the other direction. What else? And then we have momentum and momentum impulse. What else?
What was our worst test?
Average?
What was our worst?
It's probably projectile motion because it's so early in the year and it's one of the tougher topics. So if I were thinking average-wise, that's probably the one that you have most as a class. Did we do a projectile motion problem here yet?
That's what we asked in the live.
With x and y and a parabola like this?
Oh, I remember that.
Oh, I don't know, to be honest with you. I'm not sure. You want to do a projectile motion?
Yeah.
I think that's a reasonable problem to try. We didn't do one yet though, right? I'm not losing my mind here?
No.
All right. So let's go ahead and say the following. Let's say there's an object at ground level. Let's say it's a cannon, like a cannon with a cannonball being fired. Okay, and the object is fired at some angle, theta. Let's say that angle theta is, in this case, 20 degrees. And let's say that we're trying to figure out, let's see, do I want to do that? Let me think for a quick second. Hold on. Okay. We have an initial velocity of 20 meters per second. And we want to figure out if it will reach that cliff. And the question is posed that the cliff's height is, let me think, it's something reasonable. The cliff's height is 35 meters. And we are 10 meters away. These are not drawn to scale. Sorry. The cliff and that distances are not good for scaling. So we're trying to figure out if it's going to make it up 35 meters to the top of that cliff at 35 meters up there. Okay, now it's better. And we're trying to only cover 10 meters horizontally. And the question is, will it make it to the top of the cliff? So what should my unknown be? This is a tricky question. What should my unknown, like the unknown variable, the thing I'm solving for, what should it be, Theo?
X. Y.
Why?
But don't we have, what's 35?
Yeah, you think, right? And that's why it makes it tricky. You're like, I have it, 35. But what did the question ask?
Oh, asking for you.
Will you make it to the cliff or not, right? So if you get a y value and your answer is 20, do you make it?
No.
If you get a y and it's 70, do you make it?
Yeah.
So the question is solved for y. Do you see how you're almost given extra information here? So let's list our x and y stuff. Make an x and y table, please. Remember, y is unknown here. The y value is what's unknown. We know it's 35 that we have to get to, but we're trying to figure out how far we actually get. We do know x, yeah, we definitely know x. Yeah, x is given as 10, but the y is the part that is actually unknown. We know that we're trying to figure out, well, what's the height of this projectile after 10 meters? Right? If after the projectile, let me just demo this. After the projectile has, so let's say this is the cliff height. After it's been fired 10 meters, does it make it above the cliff? Or is it below the cliff? Make this 10 meters, right? So no matter what, it's going 10 meters to the right. The question is really, how high does it go after 10 meters to the right? So we know that x is definitely 10 meters. The question that's posed is, what is y? Well, to find y, we need to know what we're going to use numerically. So VIX and VIY. How do I find them? VIX and VIY. What do I do? How do I find the x component of anything? Multiply by what? What trig function? Come on, people. You just did this in math. The x coordinate always comes from which trig function? Cosine. Thank you, Drew. Somebody's awake. VI, cosine theta. And the other one? All right. This should be memorized at this point. We did this in section whatever for vectors. Okay, we did a lot with this with vectors earlier in the year. You need to know this stuff. What's the acceleration in each direction?
X is 0 and y is negative 9.81.
Well done, sir. How do you know that?
Because gravity is 9.81 and there's no friction.
And we assume no friction. Very good. That's the key here. We assume there's no horizontal acceleration, and as a result, what we're saying is there's no air resistance. Because think about it. If I throw an object to you, the air does slow it down. There's negative AX always, really. Okay? AX is always something. But we're making the assumption that it's nothing here. Okay, that it's negligible. All right, great. So can I find y? Hopefully. Good answer. Hopefully. Can I find y?
Yes.
Do I have enough information to find y? I need time. There it is. I need time. The linking variable. Good. I saw two people do this, and I saw somebody, or heard somebody say linking variable. Time is your linking variable. Every equation, not every, I shouldn't say that because one does not, but most of the equations involve time. The one that doesn't involve time involves final velocity, but we don't have that, so we can't use that one. So we need time. Okay, we need time. How many unknowns are there in the y direction? How many unknowns? Look at the y direction. How many unknowns are there? How many? Yeah, just two of them. So, Theo, what do you recommend I do?
Just do v equals x over t because there's no acceleration in x and you know
Exactly. Well done. Use VIX equals x over t. Because there's no acceleration, you could find time by switching these two positions, right? Flip-flop those. Flip-flop the VIX and the t. Now, what's VIX? It's really VI cosine theta. VI cosine theta. That's what VIX is. Do we all know that? Okay, that's VIX down there. And it's a constant. Vx isn't changing. You could even call it V bar x. I called it earlier in the year. Because acceleration is 0 in the x, so the velocity will never change. So all you need to do is take 10. I'll keep writing in here. 10 over, what was the VI? 20? No. What was initial velocity? 20? And the angle was 20?
Yeah.
Did I really do that? Jesus. I don't know how I did that. All right. I try not to do that so you don't confuse which 20 went where, you know? That was stupid of me. So VI is 20 meters per second. The angle of theta is 20. So we have 10 over the product, 20 cos 20. Put 20 cos 20 in parentheses before you type in your calculator, right? If you're going to do this all in one line. What do you get when you do 10 over 20 cos 20? What do you get? What do you got, Katie? 0.53. 0.53, and this is going to be units of seconds here. So it takes like a half a second for this rocket or this cannonball, whatever it is that's launched, to travel 10 meters horizontally. So if we know it takes a half a second to travel 10 meters horizontally, we can use this time to figure out how far it's traveled vertically. Use the same time. It's the linking variable. We'll use the same time to see if it's traveled vertically enough to surpass the 30 or 35 meter wall. I forget what we did. 35 meters? Yeah, there it is, 35. Okay, we'll see how far, or see how far it travels vertically, so we know whether or not it surpassed it. What formula should I be using for this? There are two formulas that have y in it, either x or y rather. There are two of them. Which one should I use? Go ahead, Nat. You good? I'll give you a break in a second. Let's just finish this. Oh, you just forgot?
Yeah.
You have two options. Good.
Is it a v squared f equals vif plus 2ay?
That would be okay, but we don't know VF, right? The one you're proposing is VF squared equals VI squared plus 2AY, but we don't know VF.
X equals or y equals VIT plus 1/8 squared.
Okay, and take a look and notice that I'm putting subscripts everywhere. VIY because I'm in the y direction, AY because I'm in the y direction, y because I'm in the y direction. So my goal is to figure out how far this travels vertically, so I can leave that alone. VIY is VI sine theta. 20 times the sine of 20. That's VIY times the time plus 1/2 A, that's negative 9.81, times t squared. There's a squared there, I promise. It's just kind of squeezed. Okay? Times a plus 1/2, negative 9.81.53 squared. What do we end up getting for y? And by the way, y could be positive or negative. This projectile could have been launched, and it's possible that it's already coming down on the way back down. So it could end up being negative, depending on the values. So you got 20 sine 20, right? Do that first. Then multiply that by 0.5. To that, you can just subtract or add the opposite of 1/2 times 9.81 times 0.53 squared. What are you going to end up getting for this? I doubt it's going to be near the 35. It doesn't seem like the number is even close.
I don't know what this is.
Is that right?
Negative 11.4.
Negative. I have a feeling it's not because, take a look. 1/2 of 9.81 is 4.9. Times another 1/2 is 2.5. Times another 1/2 is 1.25. So this is going to be a negative 1.25. And then this is a positive, right? So it can't be negative 11. It's not reasonable as an answer. But check again. Try and see. Guys, others should be doing this. It's the same people that practice all the time and the same people that don't make mistakes in their test. Direct correlation? I assume so. Try it, try it. Hey, it's great that you're trying it. You know why? Because come Thursday, maybe you'll forget that it's not in degree mode, and you got to change it. So check your mode right now. Although obviously on Tuesday you have your math final, so maybe you got to put it back after that. Anytime you do anything with degrees, it should be in degrees. Anytime you work in your math class and it's on radians, you're doing stuff with radians, it should be in radian mode. It shouldn't be a very high number, to be honest. No. That sounds right. 2 point what?
2.247.
It should be just positive is my guess, like just above 0. 2.24 is reasonable. Okay, not even close to the 35 meters that we needed it to get, right? So let's talk for a second. Let's say this is what the answer actually is. I believe Zoe. I think she's doing a calculator. So 2.25 is the actual y value. So tell me real quick, what should I have done to reach the 35 meter cliff? How could I have gotten there? What can I change about this problem to make it to the 35 meter height we want to get to? There are 2 answers you can give me. Well, 3 technically, actually. 3 possible answers. Come on, 1 out of 3 shot. Emma, give me 1. The angle. So 20 degrees is below 45, isn't it? 45 gives us optimal range. An even higher angle might give us even more height. So increase the angle. That's option 1. Decrease the distance x, assuming we also increase the angle at the same time. Decrease the distance x while also assuming that we are increasing the angle. But there's one else that's really just the most obvious. How do you make things go further? More speed. Is that what you're going to say? Increase VI. Increase VI is the best bet. Okay? If you increase VI, look at your values, people. Increasing VI here, increasing VI here. It's going to change this. It's going to make this a bigger number, which will give us a bigger Y value clearly. All right, good example, good example. That's projectile motion.